topic here is I want to go over the performance of the energy multiplier module with long-burn thorium fuel cycle. And before I enter into the presentation, I did want to give a brief introduction of my team members without whom I would not have been able to put up this work. Dr. Heng-Bok Choi, he is a physicist working with General Atomics for past 8 years or so, and he has joined us from KERI, the Korea Atomic Energy Agency. And before joining General Atomics, he was closely involved with the duplex fuel reprocessing methods as well as heavy water reactor research there. Dr. Robert Schleicher is the key person or the main driver of our new concept, the energy multiplier module. And Dr. Junaid Razvi, who has also contributed to a lot of this work, is well known for his contributions to the trigger reactor in the earlier days when GA had built a few across the world. In this presentation, I will walk you guys over to a very brief introduction to General Atomics, just let you guys know what we all do. And then I will lead into the attributes of the energy multiplier module reactor design, also known as the EM2. Followed by, I will hint a little bit about what are the key technology enablers to make this concept into reality, and lead into the assessment of the thorium fuel cycle. I will also talk a little bit about, if the time permits, about our breaking cycle power conversion system and the economics, which is a topic close to my heart. All right, an introduction to General Atomics. We are mainly contracting with the Department of Energy and Department of Defense. A lot of our programs today are funded by the Department of Defense in the United States. One of our major programs at GA is the aircraft launch and recovery system, wherein we are working with the nuclear navy to electromagnetize the navy, meaning thereby that we are trying to get rid of the steam propulsion systems and the launching and landing of the aircraft from the Navy ships will be electromagnetic. And we just built a prototype after 6 years of about $500 million program. We have successfully demonstrated and in fact launched an aircraft off the Navy ship recently. We also build the unmanned aerial vehicles, we call them the Predators, for many law enforcement and Air Force and Navy personnel. We are also doing a lot of research on high-powered lasers. And we also do demilitarization of chemical weapons for the Defense Department. Another key project that we've been currently working on is a very specific high energy or high speed projectile for targeted attack. Excuse me. We call it the railgun technology, and we just did a demonstration of that as well. This is a trigger reactor, which is the world's most widely used research reactors. Many of you may be aware of that as well. And we do build, among other things, power conversion systems and energy batteries as well. On the nuclear front, we are involved with fission as well as fusion research at General Atomics. We build targets for the inertial confinement fusion program for Lawrence Livermore National Laboratory. And at General Atomics, we also have a tokamak facility for magnetic fusion. It is called the ThEC15 facility, and it is the largest US magnetic fusion facility. This is the model on which the ITER program is built. So they are scaling up the G3D facility to the ITER program. And we are very much part of the ITER program as well. And we are making the 110-ton magnets for the ITER programs. We also, in our work with high-powered lasers, we also found a very neat way of punching very fine and precise holes. And that led us into a spin-off in its application to diesel engine efficiencies, which can be significantly improved. If you have very precise holes, these are of the size of a hair. We also are developing some high-powered or long-term batteries. These are plutonium batteries. I don't know much and I can't tell you much about who are the customers. These are some of our secret programs, but the goal is to have plutonium batteries which can last up to 20 years. And we also have a plant in Hawaii. This is a program funded by DARPA in the United States, wherein we are extracting oil from algae. So it's a biofuels program that we have. Now, let's talk about, coming back to nuclear energy. What are the attributes of a 21st century nuclear power plant? Well, at General Atomics, we strongly believe that, we've been hearing about many concepts where it is proposed that instead of the big, large reactors, let's bring down the scale, and by serial fabrication, serial production, and factory fabrication, we can change the economics such that nuclear power will be more economical. But we don't believe that reducing the size is the only factor. Rather, inherently in a design, we really need to focus on improving the efficiency of the reactors. So when we mean improving the efficiency, it has to be significant enough that it can be competitive. Now, if you look at some of these aspects, paramount safety, we all know that nuclear power plant safety is very important, and economically competitive designs. Waste streams, manageable waste streams, and proliferation resistance. In addition to that, I would also say that capability to utilize various fuel forms. We have to extract energy from all these fuel forms. Also, siting flexibility is an important attribute, wherein we are constrained for the most part in locating nuclear power plants close to larger water body. And if we can site them at drier locations and use dry cooling technology, but then it takes a big hit on the efficiency, which already is too low compared to combined cycle natural gas power plants today. And this hasn't been thought about much, but we have wind power and solar power these days, and we all know that the capacity factor is variable in that. And a system which can not only be used as a base load capacity, but also be able to load follow and pick up the load from solar and wind powers would be something desirable. And of all these attributes, I'd say at least the first four have to be concurrently addressed, meaning one cannot be compromised against the other for nuclear to be deployable in a large scale. Now, we know that the current, at least in the United States, the larger part of the nuclear fleet is light water reactors. And they are once-through cycles, so they require a lot of uranium, and pretty much 95% of the energy is still in the spent fuel, which is waste. So in designing our system, we were mindful of the fact that there is a lot of depleted uranium waste as well as spent fuel waste in the US, which could be reused, but with relative ease, simplicity, and something that can be deployed sooner. So with those goals in mind, somewhere around 2009, we started working on this concept. Now, GA has had a 6-year-long history in designing, development, construction, and operation of gas-fueled reactors, but they are primarily thermal reactors. We have worked with ThRiSofuel. In fact, we had the ThRiSofuel fabrication facility at the same location where I work. And we've spent a lot of years investigating that reactor, and it is a pinnacle of safety, as NRC would say, in advanced reactors. But why it hasn't seen the light of the day? That is because the fabrication of the fuel, the ThRiSofuel, is just extremely expensive. Also, it's a once-through cycle, and recycling that fuel is also a huge challenge as far as the process is concerned. And we thought that, we know a lot about helium coolant, we know a lot about, particle fuel, and we know a lot about high temperature reactors and utilizing that high outlet temperature in running a breaking cycle, a direct drive breaking cycle, for getting better efficiencies than steam cycle. However, how do we address the fuel aspect of it? and how to further improve the performance of this reactor while maintaining its passive safety features. So that's what led us to think about the energy multiplier module. Now this reactor is a passively safe reactor. It is helium-cooled, high-temperature reactor which uses convert and burn technology to achieve the ultra-long core life. In order to extract maximum amount of energy from the fuel. We thought about a multi-decade fuel cycle. And EM2 has a thermal power output of about 500 megawatts thermal, and with a 53% net efficiency, we get about 265 megawatt electrics per module. From economic perspective, though, such a reactor can be built in one module at a time, but our reference commercial plant design, which you see here, this is a layout of the overall plant. General Atomics has worked with CB&I, Chicago Bridge and Iron, which was earlier known as the Shaw Group, who are building the 81,000s for Westinghouse in 2 states in the US right now. They worked with us to define the balance of plant systems as well as the construction schedule and the construction modules for the reactor. So what you see here, this is the main reactor building. The dome-shaped feature is the aircraft shield. Under that is the maintenance hatch, and in some other pictures I will show you the cutout of the reactor system and the power conversion system. But these are basically 2 dual units packed together, so total 4 modules co-located on a site. And each module has its own powertrain and cooling tower. So the plant rating is about 160 megawatt electric. If we use, instead of evaporative cooling, dry cooling technology, meaning just dry cooling towers, then there is a compromise on the overall efficiency, but it's still relatively small and still significantly high compared to the current state of the art. So that would take us to about 48% efficiency, so the plant rating would be about 960 megawatt electric. And when I say these numbers, these are for, typical US location, probably central site. So the key features of EM2, it's a 30-year fuel cycle. It is capable of burning depleted uranium, LWR spent fuel. It can also burn weapons-grade plutonium. We are one of our projects at General Atomics is disposition of weapons-grade plutonium. It's a cooperative with Russia. And earlier our gas turbine modular helium reactor, the thermal version, was a reference design for that. And recently we have also investigated the use of thorium in the EM2, which will be main part of my talk. This reactor is capable of rapid load following because of the power conversion system. Now typically a direct drive power conversion system is at 3000 RPM because that matches with the grid frequency. What we envision here is an asynchronous turbine generator, so it spins fast almost at 13,000 to 14,000 RPM. And I'll tell you a little bit more about how we achieve that. But if it's an asynchronous turbine, then it has a capability of load following. You can pretty much control the rotation of the turbine to control the reactor power. It's flexible cycle-wise because it is amenable to dry cooling. Well, while designing this plant, we were very mindful of the largest modules that can be factory fabricated and transported to either a truck or a barge. And we've kept our envelope to the level where pretty much all components of the reactor could be factory built. You do not need a stick-built approach, and they could be truck transportable, at least the equipment, but the construction modules probably not. And our main goal is to significantly reduce the waste stream, and that is achieved from near complete utilization of the fuel because of the long core life, as well as recycling the fuel into subsequent generations with a very simplified recycle technology, such that only fission products, which are under 300 years, can be separated, and they are the only waste streams. So here's a closer picture of the primary system. You're looking at the reactor is about here. which is fueled by uranium carbide fuel. It has a silicon carbide composite cladding material, and it's an upflow core where the helium goes from top to bottom to top. The reactor outlet temperature is about 850 degrees C, which drives this asynchronous high-speed compact turbine. And the higher speed of the turbine requires a power inverter to make it synchronous to the grid. And from here, the reject heat from the three coolers of this turbine actually are going to an organic Rankine cycle, and that extracts a little bit more, energy out of the fluid, and thereby we are able to get 53% net efficiency. It's a passively safe system. These systems over here are the DRACs, the direct reactor auxiliary cooling system, heat exchanger and circulators, which is a helium to helium heat exchanger. And from there, it is the decay heat is rejected to the air by these cooling towers, which are the DRAC's cooling towers. Another thing is, in order to maintain a very standardized design, this was one of the great inputs we received from the shop, that everything above this, which is the main reactor building, should be on a seismically isolated platform, so that it can be installed in many locations only by the design of the seismic isolators, which they did in the EM2. So this slide just shows, the fuel. It's an annular fuel. It's a vented fuel concept. We use uranium carbide, and it's a very, controlled stoichiometric uranium carbide we are using here. Our baseline design is a starter fuel and a fertile fuel, wherein the starter is low enriched uranium, average enrichment about 11%, and depleted uranium as the fertile portion. And it is this depleted uranium fertile portion that we have looked at thorium as an alternative to that. These annular pellets are then inserted into the silicon carbide composite cladding. Now, even this is another area where we are intensely working in developing the cladding material which can withstand very high DPAs up to 30 years. And we have some, initial indicators of the irradiation test which are very promising. In addition to the cladding, we also need, a specific shape. So this geometry, the tubular geometry, is achieved by, fibers infiltrated with composite material. However, to make shapes and be able to machine those shapes is another challenge, and we think we'll work it through, and I'll show you some of the shapes, as well as the joining technology. And all of this will have to, go through irradiation tests and meet NRC requirement, radiation pollution requirement for fuel qualification, and we've made significant progress even in the joining technology. Now these rods then are collected into a tri-bundle assembly. So basically there are total 8,000 rods per core, the 500 megawatt thermal reactor, and about 31 rods per tri-bundle assembly. There are tri-bundle assemblies arranged for the core. So this shows some of our efforts at the fuel fabrication. We know that the long pole in any new reactor concept is the fuel. Fuel qualification has to be it's the longest pole, and it has to be addressed early on in order to understand whether our concept is really going to achieve what we aim at. So from our experience of TRISO fuel, we started with the solid gel technology and we fabricate UC kernels. We have some UC kernels, and in order to increase the speed of fabrication from this portion of the annular pellet, we are working with University of California, San Diego, where they've come up with some really good sintering aids to expedite this process. And we have produced prototypes and samples for irradiation. And as we speak, I probably think as part of our concept development proposal to the Department of Energy, we may be doing some irradiation of the fuel. So we have this infrastructure already in place at General Atomics. Now, so just to go over what are the key technology enablers for EM2. Well, first and foremost, the convert and burn core physics. The reactor, for the most part, for the majority of its lifetime, derives energy from the fertile fuel. The fissile starter is just, after a few years, as you can see, the uranium portion is the fissile inventory of the uranium, and here's the fissile inventory of the plutonium. Well, another enabler, because it's ultra long fuel cycle, another aspect is the cladding has to sustain those high DPAs for 30 years. And that's not a small challenge, but we believe we have a design that can work. Now, you can do all unirradiated property measurements, up front, but we need to look at it in irradiation environment. And one of the ways is to do an expedited testing either through accelerator systems or something where you can accumulate more DPAs in a material. But the downside of that is because silicon carbide is really good material for high temperatures and long irradiation times is because it has the self-annealing capabilities. And in an accelerator-driven system, you can't really see that phenomenon as to how this material repairs itself and goes on. The advanced fuel, especially the vented fuel concept, we don't have a huge plenum to accumulate the fission products. It's better, it performs better if we remove it so that it can maintain its integrity. And for that purpose, this, the microstructure of this fuel is also highly controlled. We need it at a certain porosity, and we need that fission products to easily drive out. So there's a lot of chemistry effort there that we're studying. Certainly the high temperature systems, that's our direct drive breaking cycle power conversion system. Now what's different in this versus the popular large GTMHR power conversion systems, because as I earlier said that because of the higher speed it's a more compact system. But in addition to that, the new aspect we brought in here is this generator. This is a permanent magnet generator. GA likes everything magnetic, by the way. So this is a permanent magnet generator. We build up to 20 megawatt motors for many of our customers, which are magnetic motors. And in doing that, we came up with a very neat filament winding technology. And what that winding technology does is it allows it to spin at very high speeds without, having a large gap for containing those, the magnetic rotor. Another slide of mine will give more idea about that. But this has enabled the compact system and the high speed. It's a PM generator. Now, though it is a key technology enabler, it is a relatively, well-known system to us since we're already producing it. It's a matter of scaling it up, and we don't see any showstoppers there. In fact, next year, we are planning to build a 65 megawatt. What you're seeing here is about a 20 megawatt motor. And we are scaling this up to a 65 megawatt generator. We believe it has other alternative applications in the Navy and wind power. And that would be right about the size of a prototype reactor that we are envisioning. So at least, at a prototype stage, we would have tested a power conversion system as well, because that's a key, technology which brings us to that very high efficiency. Proliferation resistant spent fuel recycling process. So what we see here, when I will go in more detail in the fuel design, we think that this convert and burn reactor core can be recycled into the EM2 system in the second generation of it if you only remove about 60% of the fission products. And we look forward to dry reprocessing technology similar to Gupta process or enhanced full oxidation process, which is a cyclic oxidation and reduction steps, which removes the fission products, and whatever else remains goes back into the reactor. Now, what that means is there is absolutely no heavy-metal separation. You're not separating the streams of uranium or plutonium. And that approach is a more proliferation-resistant approach. And we know very little about recycling of thorium, so we look forward to discussing with our Indian counterparts on the thorium fuel cycle. These are just showing you some of the parts of the fuel, the cladding that we have made. Here's an end plug. and the joining in between them is accomplished with this hot press that we have. This is our silicon carbide coater, in which we produce these parts. We start with winding the fiber, then putting it up on a mandrel, infiltrating it, and with computer simulations we've learned how to best infiltrate it so that the infiltration goes from inside out, because otherwise from outside in it will plug the system and it won't have a uniform thing. We are now planning to buy a full-length 14-foot coater wherein we can fabricate the full-length claddings, because when we started looking at the silicon carbide clad for EM2, that got the US government interested into exploring this concept for the accident-tolerant fuel. This program is, after the Fukushima, where some people want to get away from zircaloy clad, and this could be one way of getting away from zircaloy clad. But at the same time, because of its high temperature, maybe it will even improve the performance of light water reactors, rather with longer fuel cycles and slightly more efficiency. So, this is what we look at here. This is the existing known reserves, world reserves, and what we found is, if you look at the consumption of energy, the increase in the consumption of energy from the year 1950 up to 2000, so over a 50-year time span, the energy consumption has gone up by about 3.5 times. And on a very conservative approach, if you assume another 3.5 times, increase in consumption or increase in demand over the next 100 years, then at that consumption rate, all our known reserves would be exhausted by 2080, which is pretty startling. That's not to say that there won't be any new resources available. We will go further into, resources which are not so easily available today, but that would mean that the economics of the systems will change. So instead of using, this white portion here is the uranium utilization in thermal reactors. And if this uranium is used in fast reactors along with thorium, look at what it does. It improves, the same resources can last 25 times longer times and almost about 2,000 years. So that's one motivation of looking at thorium fuel cycle. And the other one being, well, as I mentioned, we were looking at low enriched uranium, about 12% enriched uranium, and a depleted uranium as fertile material. This is our baseline EM2 design. In addition to this combination, we have also looked at used nuclear fuel, meaning the discharge fuel from LWRs that is waiting to be put in a repository to be utilized as a fertile material in EM2 with the similar, long-term fuel cycles. In addition to LEU, we have also done parametric studies and investigated various different other kinds of materials for starter. And over here, I'm going to present the LEU and thorium case. Now, this is just, one similar picture of the reactor system. Just to give you an idea, the red portion here is active fuel, which is surrounded by beryllium carbide, it's surrounded by boron carbide as a neutron shield. We use beryllium carbide as a reference material for a reflector here, and the vessel system is the same material as light water reactor steel because it is, code qualified already. But because of high temperatures, we have to use an internally insulated vessel. So just to give you an idea of the reactor system. Alright, so this is just some key properties of the materials in an unirradiated stage. We've looked at many different kinds of fuel forms. Oxides and carbides is what we have on this chart here for comparison, because uranium carbide gives a maximum density. That is why it is one of the choice of the reference field for us. We also see that how the thermal conductivity of uranium carbide is far better at high temperatures compared to oxides, thorium or uranium. here's the cases that we have investigated. We've investigated two options of fuel loading. One is what we call the heterogeneous loading, and the other one is the homogeneous loading. In the heterogeneous one, there is uranium carbide fuel pellets and thorium carbide fuel pellets, which are separate, and there is also some enrichment zone required in the core. In the homogeneous one, on the other side, we looked at a mixed uranium thorium carbide fuel pellets. Here, it's 60% uranium and 40% thorium. And there is enrichment zoning required only in the core periphery. Then what we have looked at is for these heterogeneous core, if all else remains the same, the loading remains the same, then we look at the sensitivity of neutron economy to various coolants. The blue one is helium over here. We have also looked at liquid metal, lead, sodium, and molten salt chloride. These are the reference cases we looked at. And over here, we compare the heterogeneous helium core along with our baseline LEU-DU core and homogeneous core configuration here. And what we see here is the fuel economy is best for the gas coolant. And the difference, okay, so the primary difference between heterogeneous and homogeneous core is that the neutron spectrum here is dominated by the driver fuel, which is the UC. However, while in the heterogeneous case it is dominated by the driver fuel, but in the homogeneous case the entire core will affect that. So the spectra is pretty much similar, but just neutron economy is slightly different because of the initial fissile content over here. And this chart here shows the core life. Again, this one compares the helium, lead, sodium, and fluoride coolants, and again, keeping everything else the same, how the length of the fuel cycle we can achieve here. So helium is the longest core, which is about 23 years, and this is the heterogeneous case. The lead case is lead is about 14 years, followed by sodium 16 years, and the molten salt, it's not critical after about 8 years. This also compares our baseline core with the heterogeneous and homogeneous options, and you will see that the homogeneous option is slightly longer core fuel cycle length. It's about 28 years. This also shows the reactivity coefficient, the void reactivity coefficient, and the Doppler coefficient for all these cases that we've studied. And it looks like, gas coolant has pretty reasonable properties here. The mass balance of a few of these key isotopes here. Uranium-235, it burns fast in the molten solid cooled core. 233 production is slightly higher for the helium-cooled core. The EM239 buildup is slightly lower for the helium-cooled core, and the salt core is no longer critical after 8 years, even though the total fissile content is higher compared to the helium-cooled core here. So I think I'm running out of time, and I'm going to run fast through the remaining slides. Now, when we look at our baseline design and using thorium instead of depleted uranium, the residual plutonium is reduced by about 50% in a LEU thorium loading, which is, from a proliferation resistance point of view, a very positive feature. And also the minor actinides are reduced by about 40 to 23% in a thorium-loaded core. So just to summarize, the LEU thorium fuel cycle assessment. Parametric calculations have been performed to investigate the effects of coolant material for thorium-uranium fuel cycle. If all reactor conditions are same except the coolant material, then the helium core exhibits the longest fuel cycle, hence the highest burnout, highest use of resources, and lowest waste. The safety-related parameters for uranium thorium fuel are also not deteriorated when compared to the baseline core of uranium. The mix option is only possible or is only optimal if the thorium is less than 40%. And liquid metal and molten salt core performance would be far better if the core design and operating conditions are optimized, because we only looked at one reference case. But the advantage of helium-cooled core is the high thermal efficiency due to high temperatures and the direct drive. Well, sir, do I have enough time or should I skip? I mean, I've gone through my fuel cycle. Okay.
Short of time.
All right. So I'm just going to go to, this one slide where I will show how we look at, multiple recycling, multiple generations of fuel cycle. You have the starter and the fertile material in the first generation. The discharge from this first generation after, say, 25 to 30 years of fuel cycle, we look at some Aerox-based or oxidation-based process to remove certain fission products, and that means about 60% of the fission products. And rest of the material, balance of material, serves as a starter for the next generation. And you essentially get rid of the uranium enrichment requirement after that, which is really subjective to the success of this process. And supplement further with the amount of mass loss with fertile material, and this is how we can, in essence, keep going infinitely, but the separation factors and efficiency of the fission product removal will determine how far you can go, because after a while it just becomes economically not competitive. This is just a schematic of a full oxidation process, and this is my last slide, where I'm just comparing a levelized cost of electricity generated from 1,060 megawatt 4-unit EM squared compared to about 1,100 megawatt light water reactor, the reference design being AP1000. The source of these numbers for LWR is the annual energy outlook published by the EIA, and this takes into account the costs that are being incurred by, at the construction of the AP1000 is currently ongoing. And you see that the cost of unit electricity is cut down by almost 40%. With an EM squared type technology, but the primary one is fuel. You'll see that the fuel is slightly higher than this. And why? With all this, neat schemes. And that's because the fuel also has to be treated like the capital cost, where it has to be financed. So there's a cost of money involved with this fuel. Well, for future generations, it is really dependent upon the economics of recycling process, how this chart will look like. And just to put it in perspective, this is about where a combined cycle natural gas plant of about 52% efficiency falls for natural gas prices of about $5 per million BTU. So we really are attempting to design a system which is competitive with fossil fuels and not just alternative sources of nuclear. And that's about it.
Thank you. Well, we have run out of time, but still, since it's a very interesting and important subject of convert and burn and bleed and burn, any questions, please? One or two, please.
I have two questions. One is, you said it's 30-year fuel life.
What is that?
30-year fuel life.
Yes.
That means once we load it, right from startup line of it, we need to really not look into it. That means certainly you will be having enough failed fuel detection systems.
Right. So, this has to be with an online monitoring system. We are not, our scheme does not require any reshuffling or, rearrangement of the fuel for the entire 30 years. So from our physics studies, we see that 30 years can be met. And as I mentioned, that we really need to accumulate the irradiation data on the key, components of the reactor to get enough confidence that it can survive 30 years. But it's highly improbable that a reactor like this will be licensed for 30 years to begin with. What we look at is, similar to the nuclear Navy program, that once the reactor was, initially it is licensed for about 1 year or 2 years, and as you continue to accumulate data, your license will get extended and new systems can come in. And even as a 5-year fuel cycle, this would be a great improvement in economics, but we can push it to 30 years by demonstrating the actual performance that we bring.
The second one, you said seismically isolated primary systems. Could you elaborate on how do you?
That's more of an area of the construction firm, but as much as I understand, I will tell you, the way they are constructing the 81,000s in Georgia, Atlanta right now, and we had the opportunity to go and visit that, where they put a platform and they have the seismic isolators. They're very similar to the pivot systems, and for high-rise buildings, it's nothing new. That you put those, and then the primary system concrete slab is laid on top of it, so that every system up above it is standardized. One of the things with 81,000 is they've been licensed for a very specific design, and it's their interest that they do not make any changes to that design based on the seismic aspects of different locations. So these seismic isolators were a key portion of standardizing their design, and that's what Shaw brought to our design as well.
Thank you.
Well, thank you, Pooja. I think we don't have time for more questions, but this is a challenge. The real challenge is having long-lived fuel.
Right. We do recognize that.
Which you are paying attention to.